Thanks for coming. I'm very happy to introduce Frank Wong from MIT. He's a PhD student at MIT where he's advised by Nikolai Zeldovich and James Mickens. Frank works at the intersection of systems and applied cryptography, and today he's going to be telling us about his dissertation work on protecting privacy in web services. Thanks.
Oh, thanks. Cool. Hi, everyone. I'm Frank, and I'm a PhD student at MIT CSAIL. And today I'm going to talk about some of my PhD research on building systems that protect sensitive user data in web services. So whenever users interact with web services like Google, Facebook, or Yelp, they provide their data. This data is important and valuable both for the web service and the user. The user is willing to provide her data because she obtains value from it. For example, when a user provides her Fitbit data, she can track her health and exercise as well as compare against other users. Similarly, a user provides her data to Facebook so that she can more easily learn about the social lives of her friends and similarly share her social life. Also, buying things off Amazon and thus giving your preferences can lead to better product recommendations. So that's on the user side. So on the other side, web services actually gain a lot of value from user data. As we know, Facebook has data on your preferences, so you can make more money off ads by targeting them better. Amazon can better provide product recommendations that can lead to more purchases. So, however, there's a big security and privacy problem. Web services often handle sensitive user data insecurely. So, at a very high level, this is how a web service works. A user submits a request on her mobile device, browser, or some client to a service. The service processes that request, which might involve storing some user data or performing some computation, and returns a response. And so now Service 1 has some user data or has done some computation, and Service 1 can then also forward some of the data to a second service, or a second service might want to access data from the first service. As you can see, there are many channels where user data can leak or be compromised. For example, data can leak on the user side through the browser to an unauthorized application. Not properly handling a query can also leak private information about a user to a service. All unauthorized services can also attempt to access the data, and the data can leak from the service's database, and kind of the list goes on. This happens many times because web services often lacked cryptographically secure mechanisms to protect private user data. And so my research is very focused on solving these types of problems. More broadly, it is on building practical, secure mechanisms to protect sensitive user data in large-scale web services. And so naturally, much of my work lies at the intersection of systems and cryptography, because as I'll show in the next slide, in most of my research, I apply crypto tools to build systems that help prevent these data leaks. And so this is difficult for two main reasons, in my opinion. First, most of these advanced crypto techniques are relatively new and not well studied. And second, it's difficult to apply these crypto techniques in a practical way to achieve the system's goals. And so as a result, I spend a lot of time with cryptographers, and I'm excited to continue these collaborations across these two communities. So recall the high-level representation of a user-web service interaction. And so this is how my research projects aim to prevent data leaks in some of the channels. And so many of the projects apply crypto techniques in a practical manner to prevent these leaks. So Veil is the first platform that allows users to provide stronger private browsing semantics. It focuses on client-side data leakage, and it's based on the premise that private browsing modes like incognito mode are leaky and extremely difficult to fix in the browser alone. My next project is Splinter, which allows for private user queries to web services like Yelp or Google Maps in a practical way. And my next two projects are more focused on server-side leakage. So Cobweb and Riverbed solve the problem that the privacy policies for data and its derivatives are hard to enforce through complex applications. So we develop a practical information flow control system to deal with this in modern web services. And finally, Civ provides cryptographically enforced access control for user data. It's motivated by the fact that data is constantly shared between applications. And so for today's talk, I will focus on Splinter, which had a strong collaboration between cryptographers and systems researchers. I worked with Shafi and Vinod at MIT for the cryptography and Matei for the systems aspect. And the reason I'm focusing on this project is first, we thought it was really exciting to take a relatively recent cryptographic tool and build an efficient end-to-end private query system. And second, I enjoyed getting two different groups of researchers together to work on a project they typically would not work on. So the systems people did crypto work, and the crypto people did some systems work. And so, with this collaboration, we're able to execute on this project relatively quickly and efficiently. And so here's an outline for the rest of my talk. I'll talk about Splinter, the motivation, threat model, how we execute Splinter queries, and finally, the evaluation and some future work. So to kind of motivate Splinter, suppose a user wants to query a database to retrieve records or perform analytics. Some examples of this include searching for a patent to ensure your patent hasn't been published, looking for stock prices, medical databases to find certain diseases or doctors, and Expedia to find a flight for a trip. These queries leak sensitive user information. For example, searching for a patent on an outside database can reveal ideas in your invention. An investor's query might indicate whether they plan to buy or sell a stock. Even searching a medical database to learn more about diseases and doctors could reveal and leak potential health problems. And finally, Expedia could raise the prices of frequently searched flights. And so one naive way to solve this problem is just for the user to download the database from the service and perform the queries locally on her machine. However, these databases like Google Maps, stocks, and patents are usually hundreds of megabytes, and the user has to re-download any updates, which leads to a high communication cost. And that's especially problematic for users on mobile phones. And so this brings up the question, how do we build a practical system that can help keep users' queries private? So to accomplish this with our system Splinter, we consider a slightly modified setting with more servers and replicated databases. More formally, Splinter has two principles, the user and multiple autonomous providers, and each provider has a copy of the same public database in clear text. We assume at least one provider does not collude with the others. So on the web, many of these databases are public, such as OpenStreetMap, stocks, flights data, and for efficiency, they're already replicated across many providers. Also, unlike in the naive approach, we push some computation to the providers. And so what happens in Splinter? So a user splits their query into multiple parts and sends them to the provider. And each provider processes its share of the query on the database records and then sends back a response. And so the user takes all the responses from the providers and combines them to get the result without the providers learning the original query, unless all the providers collude. So in Splinter, our queries have low communication cost, computation, and number of round trips. And this allows us to achieve more practical performance compared to previous systems. And to do this, we use a recent cryptographic primitive, function secret sharing, to achieve this. And I'll talk more about how this works later in the talk. Yes?
So here you assume as long as there's one provider who doesn't collude with others, this will be secure, right?
Yes.
So if you relax the assumption saying there's more than half they don't collude, would that give you a better performance with a different crypto primitive?
It's not clear what this crypto primitive would look like. I mean, I think, you can imagine like, we explored using kind of information theoretic, private information retrieval. And, that kind of has different models. That, assumes like a majority or like a minority doesn't collude. It also has models where, one doesn't collude. But I think, function secret sharing allows us to kind of like get a lot of the like good communication costs and expressiveness. I mean, there could be kind of something in the middle. I mean, I think that crypto technique just doesn't exist yet. I mean, it's something worth looking into on like the theoretical side. Cool, so now I've given you an overview of Splinter. I want to more explicitly state our threat model. So the data on the providers is not sensitive and in clear text. We assume the providers are passive adversaries and try to learn the user's query, and they don't tamper with the query or the data. And we also assume that at least one provider does not collude with the others. So the contributions of this work are the following. Splinter, which is a private query system for public databases that scales to realistic applications. We are the first system that uses and extends function secret sharing, FSS, with new protocols to run complex private queries. We develop optimizations to lower CPU and communication costs, and we evaluated our system on realistic applications, which led to response times of less than 1.6 seconds for databases with millions of records. And we have to have up to an order of magnitude fewer round-trip times than prior systems that are based on cryptographic techniques such as PIR and garbled circuits. So now I've given you a motivation and threat model. I'll move on to how we actually apply FSS to execute Splinter queries. So here's the query format that we support. We support a subset of SQL, specifically projections, limiting filters, aggregates, and no joins. We support queries in the following format. Select multiple aggregates or projections from a single table where certain conditions hold, and group by or order by multiple expressions with a specific limit. It's important to note that Splinter's goals is to keep the sensitive information in the condition private and shown by in the red box with the lock. And so a more concrete example is, if we were to search for the top 10 cheapest flights for a certain route on Expedia, this is kind of an example query we would run. And the condition route equals 5, which is just an encoding of the route, leaks information about the route we are searching for. And so, we want to hide the number 5. And so in the next slide, I'll show you what conditions Splinter supports. And later I'll show you how we execute this exact query while hiding 5 and preserving privacy. So Splinter supports 3 types of conditions in the query filter. The following table is important because the algorithm that Splinter executes for query aggregates depends on the condition type. And so the 3 conditions are equality only, intervals, and disjoint ORs. The form of the condition is in the right column. E represents the column name, and CI can be an equality or interval condition. So Splinter is the first system to use function secret sharing FSS as a building block for private queries. But before we describe how to actually execute these queries, I'll describe some of the important features of FSS. So the goal of FSS is to evaluate a function in a distributed fashion without the providers learning the actual function. And so how does this happen in FSS? So first, a function is divided into k shares. These shares have the following properties. Each share can be evaluated quickly. The sum of the shares evaluated on an input is equal to the input evaluated on the original function. And given all but one share, someone can't recover the original function f. So there are efficient constructions for 2 cases. First, point functions, which is a function that evaluates to 1 if x is a specific value and 0 otherwise. And for interval functions, it's a function that evaluates to 1 if x is between 2 numbers and 0 otherwise. So as you can see, kind of at a very high level, we want to transform the query conditions into FSS-supported functions. and execute them on the database with specific protocols on top of that to preserve privacy. And in the next few slides, I will give you some specific examples how we go about executing these queries. So to better understand how FSS works in the context of Splinter, I'll start with how we perform a count query. And so suppose we want to know the number of flights for a certain route. For simplicity, let's consider a subset of a flight database with 2 columns, route and price. Each provider hosts a copy of this database like that. And so suppose we want to count the number of flights where the route is 5, but we don't want the provider to learn that we're querying for route 5. And so for reference, in this specific, when we run this specific query, the answer to this question is 2. And so how does Splinter perform this query? Well, first, we need a function that evaluates to 1 if the input is 5 and 0 otherwise. And then the user uses FSS to convert this function into function shares for the number of providers. And in this example, there are 2 providers. Some important properties of the function shares f1 and f2 are that f1 of x plus f2 of x equals f of x. And having either f1 or f2 doesn't reveal any information about the original f, which contains the user-sensitive information or value of 5. So each provider applies its share to each route record in the database. And it's important to note that the provider has to scan through every entry in the database, or else we leak user information. So here are some examples of values that will be output by the function share. All these operations are done modulo an integer field, but in our case, we use negatives for illustration purposes. And so each provider sums together the outputs of the evaluated functions and sends them back to the user. In this case, one provider sums up 21 and sends back 21, and the other one sums up negative 19 and sends back to the user, who then sums them together to obtain the answer to our original query. And so why does this work? Recall that f1 of x plus f2 of x equals f of x. This means in our example, given our function f of x equals 1 if x equals 5, across providers, the values will sum to 1 if the route is equal to 5. And since f of x equals 0 if x is not 5, across providers, the values will sum to 0 if the route is not 5. Yes?
Can f1 or f2 be 0?
I mean,
f1x or f2x in circumstances be 0?
yeah, so I mean, what it outputs is actually random. So it can be 0. I mean, it's modulo integer field, so it's kind of like 0 to kind of like n minus 1 in like in the integer field. Like if the integer field has like n elements, right? And so it could be 0 to like n minus 1. I mean, I use negative numbers here just kind of like make things easier, but it's all mod something. Cool. Oh.
Can you deal with real numbers?
So real numbers are a little bit trickier. Like you have to kind of convert them into kind of an integer first, or like you kind of have to hash them in some way. FSS works best when the kind of input is an actual integer. I mean, real numbers, you can kind of like imagine ways to kind of map some real numbers to integers potentially. Cool. Great. So now suppose that we want to perform a sum query, say because we want to find the average price for a specific route. So how do we do this? It's an extension of count. And so we want to use the same setup, except we want to do a sum price instead of count in the SQL query. On the providers, we do the same thing as count, except in addition to evaluating the function share on each route record, we also multiplied the output of the function share with a corresponding price. And because FSS is an additive function, this essentially has the effect of scaling the matching records by the price. And then each provider adds up all the results, sends them back to the user, who sums them up and gets the final answer to her query. So now we've seen how to do two types of additive queries, count and sum. Let's look at how we do a non-additive query, min, with an equality-only condition. So consider the same table as the count and sum query, and now we want to find the price of the cheapest flight with route 5 and height 5. Now we use the same function as before, generate shares and send them to the provider. So using FSS is not enough to execute this query in this particular case because FSS is an additive function. So it's not clear how it's directly compatible with non-additive queries like min. And so how do we perform this query? So our observation is that the provider can use the public information in the user-provided query to form another query. More specifically, in our example, the provider performs select min price, group by route, and this query creates an intermediate table which has the min price for each distinct route. And because this table is created using a query based on public information, no sensitive user information is leaked. And computing this table takes linear time. Then we do the same thing as sum, apply the function shares to all the records in the route column in the intermediate table, and multiply the min price column with the output of each function share. Each provider then adds up all these values and sends the response back to the user. So now let's try to do a min query with the different condition type intervals. So again, using FSS is not clear here because of the min aggregate, but now also the condition now contains multiple values that we want to match rather than a single value like the equality only condition. And so one naive way to perform this is to just perform the previous protocol we described on multiple values, but that doesn't scale well to larger interval ranges because we now have to do many of these round trips. So how do we kind of do this with a limited number of round trips? And so let's say we want to select the minimum price of several similar routes. And so now I'll provide a high-level overview of this protocol. So first, each provider uses the public information in the query, and they compute a sorted table T using the SQL query select route price order by route. Then the providers find the min price on power of 2 intervals in the sorted table T. So here, for illustration purposes and simplicity, we just show the price column in our table T. So those numbers just represent the price column that correspond to the sorted routes. So for our sorted table of 8 values, we create size 2 up to size 8 intervals. And so for the size 2 intervals, you can see we just look at neighboring pairs of values in T and pick the minimum. And then we continue this process up to size 8 intervals. And so we have a small table, but you can kind of see how we can do this iteratively for larger tables. Yes?
Does that depend on your route numbers being consecutive?
Oh, no, so our route numbers, so we sort this ahead of time.
Mm-hmm.
So, yeah, so...
So it means you can't have huge gaps in your route numbers or something like that. Like 1 and then 101 and 324 or something like that. You would have to fill in.
Oh no, so we don't. So this is just the price column. So the route is kind of corresponds to this. Your route can kind of be any range.
So how does so a user needs to know how to sort of map. Okay, so then it'll be as deep though as it'll be sort of as if a user doesn't know, I guess, what the route's numbers are, then do you have a problem?
No, so the user doesn't have to know anything about this table.
Right.
And I'll kind of show, so the next slide kind of tells you like what the server does to kind of like get the right value. So here, like the routes can be kind of anything. The routes can have big gaps or not big gaps or can be close to each other. I mean, it doesn't matter because we just sort this ahead of time. The server knows we're doing a min with an interval query and kind of performs this sorted or like caches it. And so kind of like this is kind of what the server does in the first step. Is kind of create these size up to size 8 intervals. And kind of in the next slide, I'll show you kind of what the server does to kind of return the values back to.
So for size 2 intervals, first two route numbers are, no matter it be 1 and 101, if that's what they were.
Yeah.
Right?
Yeah. And yeah, I'll show in the next one how we kind of resolve a lot of this.
Related to that, you have this price is 0. That's because that route is missing.
Oh, I mean, this is an example. Yeah, I mean, or it's free.
Okay, but you won't have a 0 fill in for a route that's missing.
Sorry?
So all these 8, they all have a route.
Yeah,
But what if you have only 7 routes? What do you do with the 8th item?
I mean, yeah, so if I only have 8, I mean, if there's kind of like a gap here, you kind of still create up to size 8 intervals. You can still do this, and so here, like, say we're missing, like, let's say we're missing 0, then this would just be 1, right? I mean, we kind of like just size it like that. And so, I mean, it's definitely easier if it's power of 2, but you can kind of imagine if it goes out here, like we want to do it to the next. So if there are 9, there will be like up to like size 16. Okay, cool. So yeah, then the algorithm proceeds in 2 rounds. So in the first round, the user wants to find the maximum and minimum indices in the price column where the route is between 1 and 5 in this particular example. And this requires 2 parallel FSS point function queries. And so for this example, we find out that the min and max database indices for those specific routes are, say, 3 and 6. And so in the next round, the client selects at most 2 intervals of each size to cover the target interval and returns the result. And in this case, we select 2 intervals from the sorted table T, marked in yellow, and one from the size, one from the size 2 interval, marked in yellow, and to cover the targeted interval 3 to 6, and then we choose 2 and 0 from the sorted table T. So it's important to note that we can't just query these 3 yellow values directly. If we do, the adversary will learn that we'll learn our interval conditions. So that's why we have to issue FSS queries for each interval table so that the server doesn't know what we're searching for. And so, but the nice thing is that we can just do this in parallel. And so in the last few slides, I showed you how Splinter can execute additive aggregates like count and sum, and non-additive aggregates like max, min, and top k for equality only and interval conditions. I won't have time to describe how we do non-aggregates with disjoint OR conditions, but at a very high level, we use private binary search and sampling on top of FSS to handle these queries. So now I've talked to you about how we execute queries. I'll show how these queries perform. So here is just some information about the 3 applications that we built on top of Splinter and their data sets, such as number of rows and size and some evaluation setup. And it's important to note that we use real data sets in these applications. Yes?
With respect to the size, are those data sets compressed? Are those sizes for on the compressed data set or in just the raw data set?
The raw data set. So here I'll present the SQL queries we perform on our case study applications. And our goal was to test various types of Splinter-supported queries on different data sets to show Splinter's expressiveness. So for Yelp, we evaluated 3 queries. Our first query, we counted the number of Thai restaurants. The next query, we executed for the top 10 Mexican restaurants near me. And finally, we find the best restaurants from a subset of categories. So for flight search, we look for an average price between a source and destination pair for a certain month and the top 10 cheapest flights for a source and destination pair. And for map routing, we find paths and nearest nodes. So these queries assume transit node routing, which is a map routing technique that's compatible with Splinter, but I won't go into too much detail on how that works exactly here. So here's a table that summarizes Splinter's performance. There are a few important things to note. We evaluate our system using 2 and 3 providers because the performance, especially the communication costs, differs based on the number of providers. So let's dive into the case studies with Yelp. you can see that these queries have pretty short response times. The communication costs are low. However, with 3 providers, we have slightly higher but still reasonable communication costs. These costs are still lower than downloading the whole database. And one thing to note is that the best rated restaurant in the category subcategory has 11 round trips. And this is because it requires a max query on a disjoint OR condition, which uses this private binary search algorithm that I didn't describe, but it ends up being log n of round trips, where n is the size of the database.
Can you explain why the communication cost from 2 to 3 then increase? One of them is 10 times, another one is 100 times, another one is like 5 times.
Yeah, so the protocol for kind of like dealing with the 3 and more server is different than the 2 server. So the 2 server has like a slightly different like FSS protocol. Like we didn't modify any of the FSS protocols, but the 2 server one is a little bit more efficient. It's a little bit slower actually in some cases, but the 3 one, it's kind of dependent on it just has more communication because like the factor is different in the protocol itself.
So the network overhead is still quite high, right? I mean, it's not much better than downloading the database.
I mean, I guess in this case, I mean, it's still pretty good. I think like if you look at the count, for example, it's only like 30 kilobytes, and so like.
But the other one, like 2 megabytes, I'll only be able to do like 10 queries, right? So it'll be roughly 23 megabytes, which was the original size of the database.
Yeah, but I mean, like, yeah, but there are updates like on the database, right?
Okay.
And so,
All the updates have to be wrapped in transactions globally. You can't have, you have to do global transactions across all the replicas to do an update.
yes. Or, I mean, you don't have to do it across everything. I think you just want to, so here you just, say we have 100 servers, you only need to pick 3. So only those 3 have to be synced up.
Sure.
Right. And so like, maybe you have like these mirror sites, maybe you always tell people like these 3 are synced up, or like these 2 are synced up. And so like it only has to be synced up between the
Probably what you want to look is like as the size of the data increases, are you better, is your slope better than downloading the database, right? So as the size of the data increases, you're going to take more and more time to download the database.
Right.
And so that's going to increase at some slope, which is probably near with the size of the database. What is your slope as you increase the size of the database? That would be certainly interesting.
Okay.
And it doesn't come up from this table, unfortunately.
Okay. Yeah.
So a couple of other questions. So is this Yelp or is it Yelp clone?
Yelp clone.
What is Yelp clone?
Oh, it's just like, the Yelp academic database I downloaded.
So it's a toy database or is it a representation of a real database?
I mean, we try to make it as close to a real database as possible, like what Yelp gave out as like what their database looks like.
Okay, and then the second question is how do you arrange for these multiple providers? Like who do you see in the real world being these providers?
Yeah, so I think in the real world you can imagine either someone volunteering to kind of host some of this, and then Yelp kind of uploads that, and they kind of pay a fee, or like Yelp itself has like a private version. And then as a result, they kind of host these multiple databases that they already have, and you kind of pay Yelp to kind of issue queries. Kind of like how a lot of APIs work now. Like when you make API calls, they charge you. You can imagine like making these types of API calls to Yelp, and Yelp charges you, but they're saying, hey, like we're not collecting information, but we need to run these servers. Here, like pay for this. So.
If those API providers are providing a service for Yelp, but isn't that in conflict with the non-collision assumption? Because on the one hand, you're assuming that they sort of talk to Yelp because Yelp is going to pay them to provide an API as service. On the other hand, you're assuming non-collusion, right?
Right. I mean, like collusion in the sense that like they're kind of like they're colluding with each other to kind of like observe this, right? Like so, our assumption is like someone will like be monitoring and like sharing information. So like I guess like ideally you would have like 2 or 3 different types of providers. Like there will be multiple people who host this, like multiple API services that like are independent, or like someone runs as a volunteer.
Okay. Can I ask a related question?
Yeah.
So for the FSS people who when they wrote the paper, what scenarios did they use?
Yeah, I mean, I think they were using the original. I think they were kind of looking at two things. So like they were originally looking at like a traditional like PIR kind of situation where now instead of looking for an index, we can kind of like we don't have to index things ahead of time. We can just like match a record directly. And they were also kind of thinking about like situations where you want to kind of compute like a distributed function. So I think they were kind of trying to think of it in like a multi-party computation sense, or kind of a maybe I just want to like farm out kind of like a computation. But they weren't very specific. I think a lot of it was they were inspired by kind of PIR and secret sharing, and kind of like seeing like can we get better performance by looking at that.
Ask a question. So, and why was join hard for you to support?
Sorry?
So you said you don't support join.
Yeah.
Why?
So it's not clear how you do FSS with join. I mean, you can kind of like think about like joining, having materialized views and joining a lot of databases. Like we can support that in that way, but we don't kind of like have a very clean way to kind of support that join. I think you have. I imagine like you can use some form of like private set intersection and kind of like work with FSS in that, but it wasn't kind of clear to us immediately how to do that join. And so for flights, we have a much larger database. To kind of find the top 10 cheapest flights between two destinations takes less than 40 milliseconds. To do average monthly price or top 10 cheapest flights only took a few kilobytes in terms of communication. And we can do map routing in about 1.2 seconds. And all these queries had less than 1.6 seconds in response time on a real network. And many queries could be run in hundreds of milliseconds. And so most queries had 1 to 2 round trips, and all queries had communication much smaller than the size of the database. And so, I mean, although we're slower than running the queries natively, Splinter can perform common web application queries very practically and more practical than prior systems. In the next slide, I'll show you how Splinter compares to other schemes. Yeah.
So the top 10 Mexican restaurant and top 10 cheapest flights, are they similar? The queries similar?
Yeah, the queries are similar. So
turns out the flight has a larger database and Yelp has smaller database, but then the communication cost for the flight is much less than the Yelp case.
sorry, so you're saying the communication for the
The flight, right? Flight talking to a larger database was only 4K and 20K. But
Right.
it's a Mexican
For each
restaurant.
restaurant, you download the PDF of the menu also. So that's
Okay, so can you comment on the difference?
Yeah, I mean, I think in the top 10, so in the top 10 cheapest flight case, like the flight table, like the flight like records itself were smaller, and then like the records for the restaurant were bigger, because the records for the restaurant, so the flight we actually return numbers, and the restaurant we actually return strings, and so it's going to be a little bit bigger. Like it's based on the kind of specific record size. So like there's a big database, but like the record size vary, and the record sizes for the Yelp was bigger than like the individual. Like there were more records in this, like a lot more, but each record in individual record size was smaller.
But don't you need to return all of them?
No, you don't need to return all of them, but you need to return a row of the database, right? And the row of the database, like the information in that database, is bigger.
Which one has more rows? Can you go back?
Yeah.
You have one slide that I remember you have more than one row. Right? The flight is 30 times more rows.
Yeah, but it's 30 times more rows, but it's only like 10x bigger, right? Like in terms of size. So that means, right? So like it has 30x more rows, but it's only 10x bigger in size, like in megabytes, right? And so each row is actually much smaller. Kind of like if you do kind of like row per kilobyte or whatever, or megabyte. And so when we return it, we have to return the whole row. Right, we want to return the whole row, like information, the whole row.
The database is like 10 times bigger than some Go.
Yes.
Does the cost of the FSS depend on the size of the things that you're
Yeah, it does. It depends on, so the performance of FSS, like how many times you do FSS, depends on the size of the domain of the input. So like, the domain of X. So if the domain of X is like 32 bits, it's, you have to perform FSS like 32 times. Because it does a bit by bit comparison.
I'm using all the 64 cores in your response time.
Let's see. So we're not using all 64 cores in everything, but we use one core in everything but the routing. The routing we use 64 cores.
Did you try use like 32 cores, less cores, or more cores? Will that change the response time significantly?
So I did for the other ones, and it didn't change. It didn't change substantially, and the reason is so there's kind of like some caching we do, and if we use kind of like so there's some caching we do because like if you know the answer to an FSS query, so for example, I do like FSS on like the number 2. Like for a given query, that will be the same answer for every time. Like the output of that will be the same every time. So like the caching, I didn't get it to work kind of across multiple cores. I tried to, but it seemed like the caching was like pretty efficient. And so if you use multiple cores, like the caching, like they compete for the cache. But it did the map routing had we use a cache. The cache hit was a lot less, and so that's why I think it worked better with more cores. Yeah.
What's the reason for choosing a machine with 64 cores?
I mean, we wanted to like have it run like on a realistic machine. I think for us, like this routing, we were saying like, hey, like if we wanted to like run it on like a machine that like an actual kind of provider would have, like
Amazon has machines with like 1 core, 2 core, 8 cores. Are they not realistic?
I mean, they're realistic, but if I'm like a big web service or like I'm a provider, I ideally have multiple machines. I don't have like a machine with like a single core, right? And so.
But why 64? That seems arbitrary.
I mean, it was a little bit arbitrary, but we kind of wanted to find like a beefy machine to see like how it scales, if certain things would scale with more cores. Sorry?
Throughput for answering these queries, or?
No, I'm not. I don't have throughput. So yeah, but most of these actually happen on like 1 core. So.
Can you say a little bit more about the caching? Like if you do FSS on the same route, what exactly are you caching?
So for let's assume like within 1 query, because like if I do FSS, like let's say the record number is 5 or something, and so I have 5, 7, 5, and so when you apply FSS to 5, it gives you kind of an output of an integer, and then that's the same if you apply FSS to 5 again. So it's like deterministic across the query. If that makes sense.
So then the server would be able to learn if I'm sending to FSS on 5. Is that correct?
No, because like it's for a given query, FSS on 5 is the same. Okay. But like a different query, it's different. But multiple records could be like multiple rows might have the same thing in like a database, and so we can just cache that. And you can kind of imagine like for flights, it could be like the same destination pair might happen like many times because there's multiple flights between 2 destination pairs.
That seems like it should tell you that you should take the database and effectively just go through it and you know what the query is, so you're going to pre-sum the database down to just having 1 entry for each key, and then you don't evaluate FSS once for each key anyway.
Right, but we don't know kind of like what the query is ahead of time, right? And so.
Right, but like you're doing this caching thing, which is essentially doing the same thing, but in a sort of more restricted way. Because you've got your query at this point, you're going through the database and you're saying, well, we'll keep this evaluation of FSS around so that we can use it again later, right? And if you, at that point, you know what the keys are, and you can run through the database once in like linear time, clean everything up so that you've got 1 evaluation for FSS for each of the keys that you're actually going to use, and then you just do it, right? It's like turning your caching around.
I see. So you're saying that if I know ahead of time what the FSS query is, like.
I'm saying you're caching.
You do, right? Yeah, basically, I mean, my understanding is you already construct a temporary table if it's a mean.
Right.
Yeah.
Right.
He's saying if you're doing sum, you could construct a temporary table of sum, then just apply FSL on each different
Right.
record.
I mean, yeah, you could. I mean,
That's-
yeah, you could. But I mean, I think like you have to do this for all the variations of the columns, right? Like, if you do, because like if I do like a sum on the, like I have to do this for all combinations of like key sum, right? Like I here in the example, it's a little bit simplistic because my table only has 2 columns, but I could have like multiple columns, and I have to do like the sum for everything. I mean, I could. I mean, you just put more storage in, and I could speed it up. Like that is a possibility. Yeah, but you would have to increase your storage size substantially. Yeah.
You wouldn't want to pre-compute all of this.
Yeah, I mean, so some of these, like you can imagine, like for top 10 and stuff like that, you can pre-compute like common ones. You can play some of these common database tricks to make this a little bit faster. Like, if you have a lot of common SQL queries, which happens like an Oracle database or like SAP database, like, if you see queries that are very common, you can kind of like pre-compute some views to make it go faster, right? Like that's definitely possible. Like here, we just don't assume that, so. Cool, so we compare Splinter to a state-of-the-art system by Olomorphin, which is most similar to Splinter in terms of supported queries. And for similar queries in databases, Splinter has up to an order of magnitude lower response times compared to Olomorphin. And the number of round trips for their system is proportional to a log factor of the database, which is about 10. And for Splinter, most queries only take a constant number of round trips and takes log n only for a very select few. And the lower round trips is especially useful in high latency networks where these types of web applications are commonly used. Yes?
Based on what's that?
So they're based on information theoretic PIR.
So you ran their code on your databases?
I didn't run their code on my database. So I kind of compared kind of like in terms of round trip times, like in terms of like number of round trips, how many it would take. Like if I ran their query, how many it would take, and how many round trips it would take. Like that's kind of like easy to compute based on their algorithm.
Okay, so just an estimate based on the round trip time that you set, assumed in your
Yeah, so these round response times are actually like them without any network latency. And so, I mean, I'm just kind of showing you these numbers to kind of see like, the range is like much different than the range here. Like that's the purpose of this slide.
And if you have zero network latency, like, I mean, why would the response time, maybe it's a dumb question, why would the response time be so high?
Because the computation is heavy, right? Like
Okay.
you're using like,
And so then you're assuming something about the hardware for the computation, right? There's some cost model for the computation that you have.
right.
And what is that? So, I mean, did you come up with, like, I'm basically trying to understand where did you get those numbers from?
So yeah, the numbers, so the top number is out of the paper, like their paper, to kind of like
Did
this,
the paper assume the same database that you had?
it was like a similar size database.
Okay, and same hardware.
It was similar hardware, yeah.
Okay. And similar network conditions.
No, they had no network conditions. So, I mean, I think, for this is kind of like, we didn't do like a very direct comparison. I mean, these numbers could be kind of like fudged a little bit, and like it would change if we actually like went and performed what they had. But I think we're like, the goal of this was trying to just show, like for them, they have to use like information theoretic PIR. Like it's a totally different model than kind of what we use. I mean, I think the comparison is, it's not 100% fair. Like I can admit that.
Okay.
But kind of, I'm just giving you a sense of like, like this is what it would potentially.
It makes sense, in some sense.
I mean,
It can be like.
sure. I mean, I think a lot of it is like we thought about like, I mean, it's just like a completely different model. Like the kind of like, we have much fewer round trips than they do. So it's like, how do we can kind of model that too. I mean, I think those are all like possible things.
But on the other hand, the computation at the server for them might be cheaper, right? Because they're just doing XORs in some sense.
Yeah, but they're not really doing XORs though, because they are doing XORs, but they have to do a lot of pre-computation or like on-the-demand computation when you use PIR, because they only have this tool that allows them to query for an index. So they kind of have to like do a lot more work. So I mean, how you kind of like, I think it's, we can kind of think of different models and convincing models to kind of think of it, but it's just, there's multiple ways we can model it. But I think just in general, kind of like the point of this is, to give you like a vague sense. I'm not claiming like, we like beat them by so much, but I'm saying like the numbers are so different. Like the point is like the numbers are so different, right? That's only the kind of point I'm trying to make with this slide.
Did you ask Olumofin for their code?
I did, but they didn't respond. So, which is, I think he had graduated a long time ago, and so this is like a 3 or 4 year old paper at least, and so.
But there are public implementations of ITPR.
Yeah.
Try using them to build their scheme.
Yeah, I mean, I didn't try, but I mean, we could have tried. Yeah, I think they use like one of these like ITPIR kind of like libraries out there. So. Cool. So there's been a bunch of work on practical private query systems, and Splinter is also related to work on PIR systems and garbled circuits. But Splinter is more practical compared to those other systems. The practical private query systems suffer from some combination of limited functionality, heavy leakage, and bad scaling. In PIR, a user can privately query for a record at index I without the servers learning the index or the response. However, not much work has been done on building very practical PIR systems that can perform realistic application queries. Typically, state-of-the-art PIR systems use multi-party information theoretic PIR for performance reasons. And even with that, these systems require many round trips, high communication costs for the type of queries that Splinter supports. But because we use FSS, we get around a lot of these performance issues. And with information theoretic PIR, to get the performance, they require that no providers collude. While in Splinter, we allow all but one to collude with each other.
In PIR, is it one provider or multiple providers?
There's different PIR kind of schemes. So like the more efficient ones, obviously like they assume none of the providers can collude. But there's a lot of so information theoretic. It's the very common ones, either like a minority or like a slight majority collude, or none collude. But you can also kind of imagine information theoretic scheme where all but one collude also, but you kind of get into like heavier communication costs. And then computational PIR is like kind of a different scheme. Like that's like a trustless scheme, right? And so their communication and computation costs are much higher.
So FSS is your core technique in some sense, crypto.
That's a core like crypto building block, yeah.
Different PIR has some other crypto primitives. So what is the key when you compare them that enables you to be better than PIR schemes?
Yeah, I mean, I think the biggest difference between I think function secret sharing is like just very different because one, it's like it's not. I think it's like expressive PIR or kind of like if you think of it because now you don't have to have an index. You kind of can match records. You can do less than greater than, which is like actually not possible in PIR directly. Like of course you can play some tricks to make it work. And I think their information theoretic PIR they do XORs and so they kind of require multiple servers. It's a different model. But in computational PIR, you have to use like public key cryptography, and we use one-way functions. So I think we kind of stand in the middle between kind of like in terms of kind of assumptions-wise between like cryptographic assumptions between information theoretic and computational PIR. So I think it's just a different model. I think it's hard to directly compare because they all provide different features. But I think the expressiveness is a very key feature and the expressiveness with the kind of like what we call antitrust or like one non-colluding server assumption is like I think very strong and an interesting kind of like model to look at.
Quick question. So the advantage of using 3 servers over 2 servers is that it's harder for 3 servers to collude because they need to all collude.
Yeah, so in that case, like, two servers can be malicious.
Two server. Is there any other advantage other than that? Other than this colluding thing, to use 3 server rather than 2?
I think the colluding thing is the main thing, and second, it's a little bit faster for like larger databases, like just because the scheme is a little bit different. But the disadvantage with why it's a little bit faster is that now you have more communication costs. Because, I mean, just current FSS with 3 or more parties require, like, the factor depends on the number of parties, and where in 2 server it doesn't. So it's just kind of how the scheme works. I mean, I think it's a very new scheme. I think there's a lot of work that kind of needs to be done both on that side and kind of like thinking more about what's going on. Cool. Yeah, and so kind of continue garbled circuits. They're a secure computation tool that allows 2 parties to privately evaluate a function, but using this tool has very high computation and communication costs in our specific setting. And so to kind of conclude the Splinter part of the talk, so current web services leak sensitive information to user queries. I presented to you Splinter, which is the first system that uses and extends FSS with new protocols to efficiently protect these queries. Splinter-enabled versions of realistic applications are fast and secure. And so kind of now I've talked to you about Splinter, I'll talk to you a little bit about future work.
Can I ask a question? So have you evaluated on the computational cost? For one query, used to be I can spend this amount of money, now with this.
Yeah, so we do have in our paper, so we kind of like look at Amazon costs. So like, one query, if it's not a maps query, it's a regular query, it costs about 0.01 cents. It's like less than a cent in terms of computational cost. In terms of like if you kind of do like a time and match. I mean, this was kind of, we did a lot of this research before the times of like serverless. And so like, I think if you run it on serverless, it could be much cheaper, but we kind of assumed like a web server, how much time of that web server it was taking. It was less than, it's like 0.01 cents.
But if without privacy protection, do you think how much it would cost?
Oh, it would be like very fast. I think it's hard to really make that comparison because, yeah, about probably like 3 orders of magnitude. Because the reason is because databases, like we can't do a lot of the traditional tricks that a database can. So like a database is like heavily engineered, like they have like scope of everything. They can do query planning that we cannot. They can have optimize the rows, and they've had hundreds of engineers work on it to like, optimize like the crap out of like a database, right? And so like, and they're very cognizant of performance, et cetera, et cetera. So
Caching, I mean, this scheme is very caching unfriendly.
yeah, it's very caching unfriendly. I mean, we do some caching, but it's like very unfriendly. Like you have to pay storage costs. But I mean, I think it's because like, yeah, that's the point. It's like in security, like you have security, you don't have a view of certain amounts of information that you own.
Yeah.
In the SQL database, if you know everything, you can kind of plan for it, right? So yeah, so here's some of my kind of follow-on work. Splinter has reduced overhead for private queries by leveraging FSS, but it's really only the beginning. I think some of you guys brought up some like kind of follow-on work or some interesting work that needs to be done. The amount of data in these web services is only growing, and users expect more expressive queries, and so it's not clear how we can scale to billions or trillions of records with this scheme. How we can have more expressive queries like joins and nots. How we improve efficiency for really 4 or more servers. Like I showed for 2 or 3, it's pretty efficient. Starting from 4, it doesn't scale as well because the FSS technique does not scale as well past 4 servers. And so, some future directions we've been thinking about and trying to make more progress on is like, how can we do some form of PIR or FSS with pre-processing so we don't have to look through the whole database every single time. So I think that helps on the billions or trillions of records part. Like, how can we design a more expressive FSS to solve the expressive queries part? Maybe this just requires new cryptographic tools for systems or new cryptographic PIR or FSS schemes. And so on a related topic, PIR and FSS and multi-party computation, MPC, have pretty strong connections. And in FSS, we wanted to hide the function, but the input was public. However, in MPC is a reverse problem. We want to hide the input, but the function is public. And so more concretely, we have 4 values, x1 through x4, and we want to compute a known function on it. However, the servers want to know the result of the function, but don't want to reveal their respective inputs to the other servers. And so, why is this useful? Organizations are storing more and more data in the cloud, and data is becoming more digitized. However, many times organizations might want to keep their data proprietary, but might be willing to compute a shared function or selectively store data. And so, for example, patients might visit different hospitals for various conditions. As a result, not one hospital has a complete view of the patient's health. So imagine this for millions of patients. Similarly, many patients might have a similar condition, but a single hospital will only have a sparse data set to do research on this. And but across many hospitals, there could be a richer data set. And so in the current world, medical researchers could be missing key insights because the data is so fragmented. But with MPC, you have a way to share and analyze this data in a secure way. And so the reason MPC is not used frequently in practice is because of poor performance, both in computation and bandwidth. So an interesting future direction is to make garbled circuit systems more efficient. Some recent work out of Berkeley has shown that garbled circuits can be used somewhat practically in systems, but they have limited functionality. The goal is to kind of expand the functionality of these garbled circuit systems and make them more practical. Similarly, there's a related FSS technique called homomorphic secret sharing, which kind of reverses this. And so for them, like the function is public, but the input is private also, and they do that for branching programs. And so, but you can kind of like imagine it being more expressive with more functionality also. And another extension for MPC is to find ways to maybe do MPC on graphs more efficiently, which is a common data structure commonly in security as kind of people try to contextualize and respond to threats. And so I'm excited kind of to continue collaborating with both cryptographers and systems researchers to solve these problems and find new systems applications for a lot of these cryptographic tools. And so I want to thank all my wonderful collaborators that's made my PhD possible. And so there are folks from systems and cryptography. And so I've also had a lot of wonderful discussions with companies like Akamai, Rapid7, and Privata to kind of help me identify and motivate a lot of these research problems. So yeah, thanks.
I have a high-level point, which is now if this technology is widely used, then the provider cannot learn some useful things like the route number 5 is hot or Thai restaurant is popular. Have you thought about any technology that still allows the provider to do some statistical learning?
Yeah, I mean, I think it's hard within this model where its goal is to kind of like hide kind of this information. If you have no information, it's hard to kind of like do some of this statistical learning. I mean, I think you can imagine kind of a world where someone kind of like does these aggregates kind of like independently. Like for example, like either anonymously or kind of like some third party does some aggregation, like using like multi-party computation or kind of something like that. But yeah, I think that's like a separate problem, and where like I have this, you can't learn it from the query directly. Like there has to be some separate system that's kind of collecting a lot of this information and kind of aggregating it. Yeah, I think here we're trying to really prevent aggregates from happening.
But in the flight case, if I did finally I purchased a ticket, that information will still can be used.
Yes.
To do marketing or adjust the price.
Yeah, I mean, in that case it would be, but you kind of prevent the problem where multiple people look for a certain flight and they raise the price as a result. Yeah, but yeah, if you purchase a flight ticket, sure.